The first thing I want to do is try to make a little bit more sense out of this expression we have for the probability that n is equal to n. So we're told this is some constant times a bunch of stuff raised to things that involve n. So let's sort of pull out everything that doesn't immediately involve n. For example, I have a 0.25 cubed. And then combine all the things that are being raised to the nth power. I have 3 raised to the nth. I have 0.1 raised to the 2n. So that's really going to be 0.1 squared raised to the n. And I have 0.25 raised to the negative n. So that's 1 over 0.25. That's being raised to the nth power. Now, let's simplify what we have inside that expression. So I have some other constant, let's call it c prime, times, well, I have 3 times 1 over 0.25. That's going to be 1 over 1/4 or 12 or 4. So 3 times 4 will be 12. Times 0.1 squared gives me a 0.12, all being raised to the nth power. And this is for n equals 0, 1, and so on. Well, as a little side note here, if y is a geometric random variable on the note set 1, 0, 1, 2, and so on, then what is the probability that y is equal to some little y? Well, it's just going to be p raised to the first power times 1 minus p raised to the y minus 1 power. Because what this means is I'm going to have y minus 1 failures before my first success. P, on the other hand, is some number. 1 minus p raised to y minus 1 is some constant times y minus p raised to y. So this is going to be some other constant. Let's call it c double prime times 1 minus p raised to the whatever my current variable value is. What does that mean for us? What that means for us is that n is going to be a geometric on the set starting at 0, 1, and so on, where my 1 minus p is the constant that's being raised to the power. My 1 minus p is 0.12, so my p is 0.88. What's the expected value of n? The expected value of n is 1 over p minus 1 in the case where we start at 0. So 1 over p if I start at 1, starting at 0 just shifts everything left by 1. So that's 1 over 0.88 minus 1, or once we evaluate this, 0.136. What is going to be the expected value of my total payment? Well, what is my total payment? My total payment, I'm going to have a bunch of loss amounts, x1, x2, and so on. How many losses do I have? Well, unfortunately, I have a random number of losses. I have n losses. But if n were fixed, I would know how to deal with this. That's sort of as a tip-off, I want to use double expectation. So the expected value of my payment is going to be equal to the expected value of my payment if I happen to tell you what is the value of n. The reason why that latter thing is sort of useful is what is my inner expectation? My inner expectation, well, I'm just summing up a fixed number of things. I'm summing up n things. What's going to be the mean of that? It's going to be n times the mean of one of them. What's the expectation of n times the expectation of x? The expectation of x is a constant, so I just factor it out. And so I get the expectation of n, which is my 0.136, times the expected value of x. So I've reduced my whole problem to finding out the expected value of x. The expected value of x, I'm just going to integrate from 40 to infinity, x times my density. So 1 over 20. Let's pull out this 40 cubed. I have 40 cubed, and I have x over x cubed, which is really just 1 over x squared. So that gives me 40 cubed over 20 times the integral of 1 over x squared, which is going to be negative 1 over x. And I'm evaluating that from 40 to infinity. So that gives me 40 cubed divided by 20 times 40. And that evaluates to 80. So that means that my expected payment is going to be 0.136 times 80. And so when I multiply this by 80, I end up getting 10.9. So I get answer choice A.